Pragya Chawla telling us about the first CHIME FRB catalog interpreting dispersion measures and scattering timescales. So take it away, Pragya.
Thanks, Paul. Okay. Hello, everyone. I'm Pragya Chawla. I'm a postdoctoral researcher at the University of Amsterdam. But the work that I'll be talking about today was conducted as part of my PhD thesis at McGill University in Canada. This work was conducted in close association with members of the CHIME FRB collaboration and focuses on interpreting the dispersion measures and scattering timescales of the FRBs that are included in the first CHIME FRB catalog. So as has been talked about in previous talks, the CHIME FRB project searches for FRBs using the Canadian Hydrogen Intensity Mapping Experiment Telescope, which is shown here on the right. The telescope looks at a patch of sky, which has an area of about 250 square degrees and is located straight overhead. And as the Earth rotates, the entire sky visible from the northern hemisphere comes into the field of view of CHIME over the course of each day, which results in CHIME having a really high detection rate, so about 3 FRBs each day. To put this in context, in the first decade of FRB searching, about 60 FRBs were discovered. The plot here shows the number of FRB detections on the y-axis and frequency on the x-axis. As you can see, these detections were made with telescopes that had different selection functions, as well as detection pipelines, so were not really appropriate for large-scale population studies. However, a month after the date on this plot was when the CHIME telescope came online, and CHIME ended up detecting over 500 bursts in the first year of operations, bringing the total number of FRB detections to 600 as of July 2019. These FRBs are reported as part of the first CHIME FRB catalog, which consists of 474 non-repeating sources and 61 bursts from 18 repeating sources. The sky distribution of these sources is shown in the plot here with RA on the x-axis and declination on the y-axis. And the different markers indicate the repeating and the non-repeating sources. The plot on the right shows the dynamic spectra of 25 of these bursts with frequency on the y-axis and time on the x-axis. As part of the CHIME FRB catalog, we characterize different properties of these bursts, which can then be used to conduct population studies. The two properties that I will be focusing on for this talk are dispersion and scattering. I'll start by giving a brief introduction of these two properties. So the plot here again shows the dynamic spectra of an FRB. And here you actually see the dispersive sweep, which had been corrected for in the plot shown on this slide. So the phenomena of dispersion causes FRB signals to arrive earlier at higher frequencies as compared to lower frequencies. And this delay is parameterized using a quantity known as dispersion measure, which is equal to the integrated electron density along the line of sight in the intervening medium. Another propagation effect is scattering, in which FRB signals travel through multiple different paths in the intervening medium and encounter different inhomogeneities along each of these paths, which results in the signal arriving at the telescope as an exponential tail instead of a sharp pulse. The scattering time scale is the time constant of this of a one-sided exponential tail fit to the pulse and increases at lower frequencies. Physically, the scattering time scale is related to the quantity known as scattering measure, which encapsulates the variations in the electron density along the line of sight using the fluctuation parameter F here. And the dispersion and the scattering measure that we observe for any FRB includes contributions from all of the media that FRB signals propagate through, starting with the local environment of the FRB source to the interstellar medium in the host galaxy, the intergalactic medium, any intervening galaxies that the line of sight to an FRB intersects, as well as the interstellar medium in the Milky Way. The contributions of some of these media are better understood than the others. For example, when it comes to the Milky Way ISM, we have an idea about the DM and scattering contribution of the Milky Way because of the models of galactic electron density, which have been derived using observations of radio pulsars. The plot on the left shows the electron density in the plane of the Milky Way as determined using the YMW16 model. As for the intergalactic medium, we can derive the dispersion measure contribution of the IGM if we know the redshift of any source and vice versa. This relation, the DM redshift relation, is shown in the plot on the right here with DM on the y-axis and the redshift on the x-axis. The DM redshift relation depends on the cosmic baryon density, and here has been derived using the Planck cosmological parameters. As you can see, FRBs which have measured redshifts and DMs and are indicated by the colored markers here do follow this relation, although there is some scatter around it due to the inhomogeneities in the intergalactic medium along different lines of sight. As for the scattering, which is caused by the intergalactic medium, that has been constrained using cosmological simulations and is found to be much less than a millisecond at 600 megahertz. So 1 millisecond is the instrumental resolution of the CHIME FRB system. Therefore, in all of the analysis that I'll be describing now, we do not really consider intergalactic medium scattering because it's not expected to affect our observations significantly. So while we have some idea of the DM and scattering contribution of the Milky Way and the intergalactic medium, the contribution of intervening galaxies, the host galaxies of FRBs, as well as their local environments are poorly understood. But this gives us an opportunity to use FRBs as probes of electron density. This was initially done by inferring the DM and scattering contribution of different media for FRBs which were localized to their host galaxies and had redshift measurements. Later on, there were also population synthesis studies that were performed on a small sample of bursts, so about tens of bursts detected with the Parkes and the ASCAP telescope to constrain which of these media contributes dominantly to FRB scattering. Now with the CHIME FRB sample, which has 535 bursts, we can really improve on the previous populations studies due to better statistics. And that is what we try to do by interpreting the DM and the scattering distribution of the CHIME FRB catalog using a population synthesis analysis. So the distributions that we'll be focusing on are shown here. So the plot on the left shows the observed DM distribution in the CHIME FRB catalog. It is important to note that this is not the true DM distribution of the FRB population because there could be detection biases in our real-time pipeline that prevent bursts from certain DMs from being detected. So we characterize these detection biases by injecting synthetic signals into our real-time detection pipeline and determining the detection probability of a burst having a given DM. This selection function is shown here in the top panel as a function of DM. And in order to get the intrinsic distribution of DMs for the FRB population, we can just divide out the observed distribution by the selection function and end up with the intrinsic distribution, which is now shown on the right as a blue histogram here. We can do a similar thing for the scattering time distribution. Again, the left panel here shows the observed distribution of scattering time scales in the CHIME FRB catalog. And the top panel shows the selection function. The selection function here looks a lot different as compared to the selection function in the DM because we have very low detection probability for FRBs which are highly scattered. Now, when we divide the observed distribution of scattering time scales by the selection function, we end up with the intrinsic distribution of scattering times for the FRB population, which is shown on the right. As you can see, this suggests that there is a large population of events that are highly scattered, so have scattering times greater than 10 milliseconds. And that's because we have detected a few of these events with really high scattering times, even though we have a very low probability of detecting any of these bursts. So the population synthesis study that we performed to interpret these DM and scattering time distributions simulates the expected DM and scattering of the different intervening media that FRB signals propagate through. So for the Milky Way and the IGM, these contributions are simulated based on the galactic electron density models, as well as the cosmological simulations. But for the other media, the intervening galaxies, the host, and the local environment, we test different models of electron density in each of these media in order to see whether we can reproduce the distributions that we see in the catalog. This population synthesis study has been presented in a recent paper, which has been submitted to the Astrophysical Journal and is available on the archive in case anyone wants to take a look at more details about this study. So as for the host galaxies, we assume FRBs to be located in different host galaxy types, ranging from spirals to ellipticals to dwarfs. We also assume different spatial distributions of FRBs within their host galaxies. And these spatial distributions differ in terms of the potential progenitor models. So for example, if FRBs were giant radio pulses from pulsars, then we would think that they would be distributed in their host galaxy like pulsars are in the Milky Way. So we simulate a large sample of FRBs and the electron densities in their host galaxies. These host galaxies are assigned random inclination angles, so some are face-on, some are edge-on, and all configurations in between. And then we integrate the electron density distribution from the FRB location to the edge of the galaxy to get the host DM and scattering distributions. So a histogram of the simulated host DMs is shown on the right. As you can see, dwarf and elliptical galaxies have much lower host DM contributions as compared to spiral galaxies. The reason for dwarf galaxies having low DM contributions is due to their small sizes, because you don't have enough path length through the galaxy to accumulate the number of electrons needed to provide a high DM. As for elliptical galaxies, the DM is lower because of the lack of free electrons in these galaxies. As for spiral galaxies, we consider 3 progenitor models, and magnetars have on average the highest host DMs. And that's just because magnetars have lower scale height, so they're located closer to the plane of their galaxy, and that's why encounter many high electron density regions close to the plane, resulting in a high host DM contribution. We see similar trends when we simulate the scattering times from the host galaxy ISM. And since we do not have much idea about how turbulent elliptical and dwarf galaxies are, in order to simulate these scattering times, we assume the turbulence to be the same as that for the thick disk of the Milky Way. So once we have these different DM and scattering distributions for different host galaxies and progenitor models, we add these contributions to the contribution from the Milky Way and the intergalactic medium to see if we can reproduce the observations that are included in the CHIME FRB catalog. So in blue here is the selection corrected scattering time distribution for the CHIME FRB catalog. And as you can see, none of the simulated distributions are able to match this population of highly scattered FRBs that we see with CHIME. This motivated us to consider additional sources of scattering. So we start by adding high electron density local environments to each of the simulated FRBs. These environments are modeled based on observed DMs and scattering for galactic pulsars and have dispersion measures ranging from 10 to 300 units. So in order to show how much difference does the high electron density local environments make, here is the cumulative distribution function of the DM and the scattering time from the CHIME FRB catalog in blue. and a configuration in which FRBs do not have high electron density local environments shown in green. Once we simulate FRBs located in these high electron density environments, we find that the scattering distribution starts to match a bit better with the catalog, although it is still inconsistent. We then place these FRBs in even more extreme local environments by increasing the minimum local DM to about 50 units. And while this better matches the observed scattering times, it ends up resulting in a lack of low DM FRBs, as is shown by the difference between the red and the blue curves here. This implies that if we want to match both the DM and the scattering distributions of the CHIME FRB catalog simultaneously, FRBs must inhabit environments with higher scattering per unit DM than has been inferred for galactic pulsars.
So 2 minutes, Pragya.
Yeah, thanks, Paul. We also test another source of scattering, and that is any intervening galaxies that the line of sight to an FRB could intersect. There have been models suggesting that cool ionized clumps in the circumgalactic media of these intervening galaxies could cause intense scattering. Although the predictions from these models are greatly uncertain, varying by a few orders of magnitude. But we still add this additional source of scattering to the FRBs in our simulations and find that while this is able to better match the population of highly scattered FRBs that we see with CHIME, there is still room for even like high electron density local environments to contribute to this scattering and be able to explain this distribution. So I leave you with the summary now. So the catalog 1 is published and includes 535 bursts. And the calibration of selection effects provides evidence for a population of highly scattered FRBs, which are difficult to reproduce with our current models of host galaxies and local environments, which suggests that FRBs must inhabit environments with stronger scattering properties than those which have been inferred for galactic pulsars. The way forward here would be to analyze the scattering budgets of localized FRBs in greater detail, because that would allow us to interpret the scattering properties using information that we know from observations at other wavelengths about the FRB host galaxy and how the local environment looks like, to be able to disentangle the contribution of each of these intervening media. That's all from me, and I'm happy to take any questions now.
Hey, thank you, Pragya, and a round of applause on behalf of everyone. So we have a question from Bal Chandra.
Yes, Pragya, very interesting talk about the propagation effects from different types of medium. I was just wondering, have you sort of accounted for extreme scattering events taking place in the IGM or in the either in the intervening hosts or in the host galaxies to try and match the scattering distribution better without affecting the DM distribution?
So as far as I know, I believe the extreme scattering events cause increase like in the flux densities and don't really show up as an enhanced scattering timescale. Maybe there's something that I'm missing there.
Not necessarily. They would lead to, especially at lower part of the CHIME band, 400 to 600, they could lead to, so I don't know, you calculated some reference frequency, I presume, the scattering, right?
So this was 600 megahertz for us. Yeah.
Yeah, so they could, in principle, change the spectral index of scattering, and that could lead to a change at a given representative frequency.
Okay, yeah. So like in our case, we model all of these 535 bursts assuming an index of -4. The reason we kept the index constant was because there were some bursts that were like fairly narrow band, in which case it's hard to fit for an index like for the scattering. So we only had like one particular index for all of these bursts, and like once we had that, we did not really consider like anything that could change the spectral index. So, so to answer your question, we have not accounted for extreme scattering events like here, like in these simulations. But I believe that there is about like 50% of the population that we are seeing that has really high scattering, and the probability of with which we see extreme scattering events, like along the line of sight to like different pulsars in our galaxy, I believe that is fairly low than 50%. So even if we include those in the simulations, we might be able to explain some of these highly scattered FRBs, but I believe there is still going to be room for FRBs having more extreme local environments as well.
Okay, thank you.
All right, I think that brings us to the end of the time for questions. So Jason, you can ask your question in Slack or in GatherTown afterwards. So our next talk is Noble telling us about low frequency wideband timing on GMRT. So take it away.
Yeah, hello, can you hear me?
Yes, I can hear you.
Yeah, okay, great. Greetings, everyone. I'm Nobleson. I'm a PhD student at Plenary, Hyderabad, India. I'm presenting this work on behalf of the NPTEL collaboration and co-contributor Tim Pinucci. So this is currently a work in progress. So let me start with an introduction. Pulsars are rotating neutron stars which emit pulse radiation observed mainly in radio wavelengths. So the radiation then travels through the interstellar medium where it gets dispersed due to the presence of free electrons, causing delay in the time of arrivals of pulsars as a function of frequency. So the dispersion delay is characterized by the dispersion measure, which is proportional to the cumulative column density of free electrons in the interstellar medium. So we can get precise measurements of the DM by measuring the pulsed time of arrivals simultaneously at different frequencies. And in the search of nanohertz gravitational waves, high precision timing is very important. And typically these are obtained using observations above 1 gigahertz. And the DM is calculated using quasi-simultaneous narrowband observations and 2 or 3 widely separated observing frequencies. In such measurements, the alignment of the fiducial point of the pulse at different observing frequencies is critical because this can cause systemic errors in the DMs and other pulsar timing characteristics. Furthermore, there are extreme scattering events, DM events, and profile changes which are seen in some of these pulsars, which can complicate this further. So with the availability of wideband receivers and backends, so this presents a new possibility for high precision timing using wideband timing approaches. And these techniques generate high precision TOS while simultaneously estimating DM fluctuations as well. So pulsars are bright at frequencies below 1 gigahertz, and the higher signal to noise ratio at these frequencies could potentially yield higher precision TOS. However, the electron distribution in the ISM has a dominant effect on the pulse shape and time of arrival of the pulse signal from these pulsars at low frequency. Scattering due to ISM broadens the pulse signal. It also delays the pulse by a factor roughly proportional to its width, leading to inaccurate timing measurements. So the timing variability of the DM due to dynamic nature of the ISM, it also introduces a correlated noise that is covariant with the signature of the stochastic gravitational background. So application of wideband techniques to such data will then provide a robust way to correct for profile evolution with frequency as well as ISM noise, including the corruption of data by abrupt ISM events. And this promises to make low frequency PTA observations as useful as the high frequency observation. So in this work, we describe the application of this technique to low frequency observations, like below 400 megahertz from 300 to 500, which is complementary to recent application of this method in the 400 to 800 megahertz frequency range using CHIME and GBT. So the pulsars used in this study are these 5 pulsars listed here. So these are observed in the cycle 39 of uGMRT. This is covering a period between November 2020 to April 2021. Since our goal is to demonstrate the application of wideband timing at low frequencies, only band 3 data, which is from 300 to 500 megahertz, is used for the work presented here. So I'll try to briefly talk about wideband analysis. So in the wideband analysis, the data processing is performed in 3 stages. So in the first step, a 2-dimensional template is created. This contains the pulse amplitude as a function of frequency and phase. So each phase frequency subintegration in the data set is called a data portrait. The starting point in construction of this portrait is nearly same as the traditional timing analysis, which consists of an iterative procedure of adding all the significant total intensity profiles of all frequencies in a given band. But instead of only aligning each data portrait compared to a constant profile using only a phase shift, each profile is also rotated by a factor proportional to the inverse square of its frequency. So by doing so, we can minimize the dispersive delays caused by DM changes, which could smear the average portrait. So in the next second step, a principal component analysis decomposition of the average portrait is performed, and which is followed by a reconstruction of the template profile based on the significant eigenvectors. So we apply a PC principal component analysis to the average portrait profiles, whose dimensions are n-chan cross n-bin, which encompasses the observed bandwidth with pulsar profile. So we choose the top 10 eigen profiles ranked according to their signal to noise ratio. The mean subtracted profiles are then projected onto each of the eigen profiles to obtain a set of coordinate coefficients. A low degree spline function is used to fit these coefficients, which is parameterized by frequency and encompasses the evolution of the pulse profile shape. So by linearly combining the eigenprofiles EI with the spline coefficients BI and adding it to the mean profile, we can get a template profile T nu at any frequency nu. So using this template, in the next step, the DMs and the TOAs are calculated. So the TOA and DM pair from each observation are obtained by minimizing the chi-square. So this is similar to a conventional time of arrival likelihood, except that here there is an additional index n, which labels the frequency channel with the center frequency nu n. So the two fitted parameters are phi naught and dm, and these are fitted for each profile, and these are constrained to follow the cold plasma dispersion law. So a likelihood that is implemented in the pulsar timing package tempo effectively uses these wideband DM measurements and TOAs as priors on the DM model parameters. Therefore, in this analysis, we are able to obtain DM time series and residuals with respect to the fitted ephemeris. So here I'm presenting the timing residuals. On the x-axis we have the MJD, modified Julian date, and on the y-axis we have the residuals. So these are the residuals for the 5 pulsars in the study. So the median TU uncertainties obtained at 300 to 500 megahertz are given as below, with 1939 having 0.02 microseconds to 1643, which has 0.66 microseconds, with the post-fit RMS of 0.04 to 0.53 microseconds. So we wanted to compare our results with the high frequency data. So we compare our results for these same pulsars now with the nanograv 12.5 year data release. And as we can see, for most of the pulsars, they are in the range of 1 to 2 times, and for 1713 it is about 11 times. So we also obtain DM measurements for each of these pulsars, and we also wanted to compare the DM's estimates obtained from wideband timing with the already published DM values for the same pulsars using the narrowband timing method. So the black points are the wideband timing results, and the red points are the narrowband timing results. And we can see that they are consistent within the error bars for all the pulsars. And the DM precision ranges from 0.03 into 10 power minus 4 centimeter minus 3 PC to 1.15 into 10 power minus 4. So these are the ranges that we get. So in summary, using the dispersion formula, we can show that the precision in DM measurements obtained in our 200 megahertz bandwidth, that is 300 to 500 megahertz, is at least an order of magnitude better than the wild high frequency band, 700 to 4000 megahertz, assuming a typical 1 microsecond TOA errors. So these are theoretical calculations. The application of wideband timing to this band can provide post-fit residuals comparable to high frequency data by taking care of ISM effects considerably. The wideband technique also utilizes the signal to noise ratio of the entire wideband observation to provide a single high precision TOA for each epoch. Unlike the narrowband technique where we have multiple subband, multiple TOAs for each epoch. So this significantly reduces the dimensionality of subsequent Bayesian analysis, which is employed for the detection of gravitational waves. And as pulsars are much brighter at these frequencies, this enables high precision measurements with smaller observation duration per pulsar at low frequency. Also with a higher cadence than currently employed with the same telescope time. And since several weaker millisecond pulsars also can be included into the PT ensemble, this can provide a more uniform sky coverage for useful sampling of the Hellings and Downs overlap reduction function, and also significantly increase the sensitivity to the stochastic gravitational wave background. So, and with the square kilometer array telescope also becoming available in the near future, the wideband techniques are likely to play a very important role in the analysis of data from MSK. So this is all that I have for this evening. Thank you for your time.
Sorry, just didn't want my 2-minute timer to go off. So thanks, Nobleson, and I'll give you a round of applause on behalf of everyone. So are there any questions? Okay, so if anyone has any questions in the future, feel free to ask in Slack. And so our next talk is Rob Kavanagh talking about star-planet interactions at radio wavelengths. So take it away, Rob.
Okay. Is that all right? Yeah.
Yeah, that's good.
Okay. Okay. Hello, everyone. Thank you all for sticking around. For those who it's late at night for, like it is for me. So my name is Robert Kavanagh. I'm a final year PhD student at VIII Observatory. And today I just want to briefly talk about or give an overview of work we've been doing over the last couple of years on modeling star-planet interactions and how these can produce detectable radio emission. And so a lot of this work has been done in collaboration with the people down here below. So just a quick outline of the talk. I'm going to talk about two different types of star-planet interactions that can produce radio emission. The first of which is from exoplanetary magnetospheres. So this is inspired by what we have seen in the solar system for Jupiter, for instance. And then next of all, I will talk about this alternative emission mechanism, which is kind of gaining traction in the literature, which is more indirect. It's not emission from the planet itself, but rather emission that is induced in the star due to an interaction with the planet and the star's own magnetic field. And then finally, I'll just talk about some recent results that are undergoing review at the moment that is kind of looking at interpreting recent radio observations, such as those becoming available from LOFAR, and how we can maybe in the future infer the presence of planets from these radio observations. So the first of which that I mentioned was radio emission from exoplanets themselves. So the idea with what happens here is that, okay, so we have a planet orbiting a star, and so low mass stars lose mass through their stellar winds, which are magnetized hot ionized plasmas. These flow out and interact with the planets. And so if there's a planet there with its own magnetic field, just like what most of the planets in the solar system have, we can have the stellar wind interacting with the planet's own magnetic field and causing reconnection to occur in the night side of the planet's magnetic field. So this is just these lines highlighted in red here. And the idea is that this reconnection releases energy, which in turn accelerates electrons along the magnetic field lines towards the poles of the planet. And now we know from radio emission theory that when electrons are accelerated along magnetic field lines, they circulate and produce electrons such on Maser instability emission. And so what's observed in the solar system for all the magnetized bodies is the following. So on the x-axis here, we have the incident power of the solar wind, and then on the y-axis we have the power of the radio emission produced from this process. And so what's observed is that these two quantities are directly proportional to one another, and this is referred to as the Radiometric Codes Law. Now, the idea with this, which has been talked about for quite a while, is that it's like since the 90s at least, is that as we go to other exoplanetary systems like hot Jupiter systems, so these are systems where you have a Jupiter-sized planet very close to its host star, and as a result, it's being bombarded with a stellar wind. So the stellar equivalent of the solar wind, it's being bombarded with that, but at to a much greater extent. So these planets feel a much more powerful wind than any of the planets in the solar system. And the idea with that is that, okay, they're being subjected to much higher stellar wind powers. And so if this trend holds at these more high energy examples, then much more radio emission could be produced, like many more orders of magnitude. So, you know, anything from 100 to 10,000 times stronger. And if that's the case, well, maybe we can detect some of these. So here's an example of a specific hot Jupiter host that we looked at a couple of years ago, called HC 189733. And so, as I said, the stellar winds are magnetized hot plasmas, and these are driven by effectively magnetic energy, which is deposited into the corona, or the upper atmosphere of these stars. Now, what you can see here on the top is the magnetic field map of the surface of the star at 3 different epochs. And so this is possible through a method called Zeeman Doppler imaging that some people may be aware of. And so the idea with this work was that, okay, we know that this star has a magnetic field that is very complex and it's quite strong, and it's also varying over time. And so the idea of this was that, okay, this change in magnetic field could drive, not only could it drive a wind which can interact with the planet which we know exists there, but it could also produce time varying radio emission from the star. So you can see then on the bottom panels, so this is kind of the cornerstone of my PhD, is doing stellar wind simulations, which use these maps as an input. So this is the main ingredient for these kinds of things. And these are 3D MHE simulations based on these magnetic field maps. So this gives us a 3D picture, a realistic 3D picture of the star's plasma environment. And you can see that the orbit of the planet here is marked in a circle, and you can also see that, okay, I've plotted just the velocity of the stellar wind. So you can see between the years, the image changes quite a bit, and as well as that, it also is very asymmetric. So as this planet is orbiting around over a short space of time, it's going to be subjected to a wide variety of stellar wind pressures, or whatever way you'd like to think of it. And so using this same radiometric Codes Law that we observed in the solar system, we were able to produce the flux density that the planet would emit if we could observe it at 25 megahertz. And so, as you can see here in the top left, that this emission will be visible for most of the time, which is quite promising, obviously. But one interesting result that we also found in this work was that the planet orbits through these regions that are optically thick to radio emission at 25 megahertz. And so as a result, inside this kind of green band here, that the radio emission from the planet will be significantly absorbed and probably unlikely to be detected. There are more details about this in this paper from about 2 years ago. I just wanted to quickly mention that there were detections announced at the end of last year from Tailbu, which is another system similar to this, which is host to a hot Jupiter. And it could be indicative of this kind of emission. So, you know, thanks to facilities like LOFAR, this kind of stuff is becoming a reality, and hopefully we'll be able to nail down a confirmed detection in the next couple of years. Fingers crossed. So the next type of emission that I want to talk about is this more indirect emission. And so this occurs, or this is analogous of what is observed between Jupiter and Io in the solar system. And so Io orbits Jupiter's plasma environment in a subalpha orbit. What this means is that basically just this top left equation. So the relative velocity between Io and then the outflowing plasma, or well, it's not really outflowing in the case of Jupiter, but so when this relative velocity is just less than the alpha velocity, which depends on the density and magnetic field strength of the plasma, Io can perturb Jupiter's magnetic field and produce alpha waves. Now, these are mechanical waves that travel back towards Jupiter and carry energy. And so then the idea is that this energy can be converted into ECMI, similar to what happens in the reconnection type scenario for magnetized planets. The idea with this is that you could apply this to a star and a planet type scenario. So Jupiter, or the star is taking the role of Jupiter and the planet's taking the role of Io. And now the radio flux that can be produced in these interactions was derived by Sarah a couple of years ago. And the main thing to bear in mind here is just that the flux density produced depends on the radius of the planet, and then this quantity here in red, which just depends on where the planet is or how far out it orbits. So these interactions occur in this kind of closed field region of the star's magnetic field. And if the star has a stronger magnetic field, this region tends to extend out further. So the idea is that for stars like M dwarfs, which have very strong magnetic fields, we could have a wide region or a very extended region around the star where these interactions could occur. So at the start of this year, we published this paper where we developed a model to use the information we get from stellar wind simulations. I'll just let this play while I talk. So this model is using the information from stellar wind models, and then we're able to use this expression from Sarah to produce the flux density that we would observe if this interaction is occurring. So on the left-hand side, you can see this is a stellar wind simulation of this nearby M dwarf called AU-MIC, and it's host 2 planets, which are outlined in black here in these circles. And so you're seeing the inner planet orbiting the star, and then this line connecting the two is the magnetic field of the star itself, which we obtained the structure of from these stellar wind simulations. And so you can see when the planet orbits inside this white line, which is the alpha surface, and so inside this white line is where this condition for planet-induced radio emission to occur is satisfied. And so inside here, we can have these alpha waves traveling back towards the star and producing radio emission. So down on the bottom left, I show kind of like a dynamic spectrum for the emission that we produced using this model. And then here I'm just comparing it to these observations of another M dwarf called UJ1151, which was published by Harish Vedantam and collaborators, again at the end of last year. And so you can see that the magnitude of this emission is very similar, which is quite promising. And so another thing that, I'm actually going to skip this because I'm going to be late otherwise. And so kind of the motivation for developing this work was kind of this knowledge that, there's this LOFAR 2-meter sky survey, which I think we're going to hear about in the next couple of days. And so this was a survey done across a couple of years, and part of like a subset of the results from this was these 19 M dwarfs, which were observed from 120 to 167 megahertz. And many of, or just based on the combination of the brightness, temperature, and polarization fraction of this emission, many of these could be potential candidates for this type of emission. So, it's kind of, the timing of this was good for us in that we were able to, use this model we developed to start looking at some of these observations. And so one of these that we were looking at was WX-UMA. So this is another M dwarf. It's quite nearby, it's just under 5 parsecs away. And so here on the top left, you can see the flux density over 3 different epochs. And so 3 8-hour windows were obtained. And so we were thinking, okay, WX-UMA, it has no known planets around it, right? So that's the key distinction between this and AU-MIC. And we asked ourselves this question of, okay, if we place a hypothetical planet around this star, can we reproduce this radio emission? Because if so, maybe we can carry out follow-up searches and stuff like that. And it's just a nice proof of concept of this kind of theory. So again, on the right here, I'm showing the magnetic field of the star, which was mapped about 11 years ago at this point. And again, what we did was we used this to produce a stellar wind simulation of WXUMA. And so what we did was we placed a planet inside around the star in this closed field region. So in where these white lines are here, with at a certain distance and with a certain radius, and then we produced what this planet-induced radio signal would look like. And so then for each value that we put in, we compare it and then see which one looks decent. And what we got was this. So we were able to reproduce the emission quite well with the planet that's about 20% the size of the Earth orbiting the star, quite close, within or about 3% of the distance that the Earth is from the sun, which is very exciting. This is a great proof of concept, and we could apply this model to many like recent and upcoming radio observations and potentially identify stars which could be host to planets that we haven't detected yet because of various different issues like stellar activity and stuff like that. So I'm just going to leave conclusions here for you to read, ponder over. Maybe if people have questions, I'd be happy to take them. I'd also be happy to talk about any of this over Slack afterwards if you prefer. But yeah, I'll stop there. And thanks very much for the organizing committee for having me.
Okay, thank you very much, Rob, and round of applause, Rob. So are there any questions for Rob? Joe, I see that you have a question.
Yeah, thanks, Rob. Really interesting results. I was just wondering how sensitive your models are to, so with WXUMA, it has a dipolar kind of magnetic field. I guess that's long lasting, right? I don't know how long, like, does the structure change over a 10-year time period with these types of M dwarfs and stuff like that? I'm just thinking like you're extrapolating with the assumption in 10 years, this is the same topology. Is that realistic with a star like WXUMA?
Maybe not. So there was a map of the star in 2006, and so this is the main one that we use in the paper. And then there was another one reconstructed from observations in 2009. Mm-hmm. So the field strength does change a bit. I can't remember if the polarity switches or not, but I would imagine that that dipolar component is still very much dominant. It might turn upside down, but that's why it would be nice to apply this kind of stuff to a star. I mean, a lot of these stars, they have maps over like much shorter time intervals. They might have like 10 or 20 maps over a couple of years. So applying to something like that would obviously be ideal.
And in terms of the wind, because you have to make some assumption on the wind properties, right? What do you use to constrain for that?
So for WXUMA, it isn't one of the lucky stars with a stellar wind mass rate estimate, but what we did for this was we just used these kinds of trends that are emerging between the mass rate of these stars as a function of their surface X-ray flux. And so by looking at the observed X-ray flux of the star, surface X-ray flux, we can estimate a kind of ballpark estimate for its mass rate, assuming it agrees with these trends.
Cool. All right. Well, I need to read your paper, which is on my to-do list tomorrow. Thanks, Rob.
Hey, go ahead, Harish, with your question.
Yeah, I was thinking, your talk got me thinking that maybe what will be interesting is to find a system where we have a Zeeman Doppler imaging map. There's a known exoplanet within the subalphanic, regime, and actually just totally test out this prediction, right? Let's say we know from UV measurements or something, what the mass loss rate of the star is. So
Yeah,
it's all aspects of it, like in one grand test, in one system. So maybe AU MIC is one of them. Like, are there any others which you can make predictions for, especially in the northern sky?
You're asking a non-observer about what hemisphere is starting.
No, it doesn't matter. Even southern is fine, right?
Yeah, I don't know. Even for AUMIC, its mass loss rate is really quite constrained. That was kind of the idea behind looking at those low and high mass loss rates, was that we were kind of trying to cover the range of possible mass loss rates. Yeah, it's pretty limited. Like, a lot of these stars with measured mass loss rates don't have ZBI maps. That's the problem. So
yeah.
Yeah, I would have to have a closer look at the current values, but I can't think of any good examples right now. I think getting recent radio observations of AUMIC would be very nice, and I think people are trying to do this at the moment.
Yeah.
And
I
it's
mean,
nice
we can take this offline, but it's kind of interesting to come up with like one system which is known really well that the models can be tested.
Yep. Yeah, definitely. I agree.
Thanks.
Okay, thanks.
All right, thanks again, Rob. And so next up, we've got a talk from Barnali Das, and I will be playing a recording, but she is here for questions afterwards. It's just early, so prefer a recorded talk. So let me share my screen. Make sure I'm sharing sound. Yes. Okay. So,
hello, everyone. My name is Barnali Das. I'm a postdoctoral fellow at the National Center for Radio Astrophysics, Tata Institute of Fundamental Research in India. So today I'll be talking about the mystery of main sequence radio pulse emitters and our attempt to solve that mystery. So main sequence radio pulse emitters, or MRPs, are magnetic early-type stars that produce highly directed coherent pulsed radio emission. So these magnetic early-type stars are characterized by their presence of very large-scale surface magnetic field, which are often of dipolar topology in most of the cases. So the emission mechanism behind this coherent pulse radio emission is the electron cyclotron major emission, or in short ECME. ECME is produced near these north and south magnetic poles of these hot magnetic stars, and one of its primary characteristics is that the frequency of emission is proportional to the local electron gyro frequency. As a result of that, the higher frequencies are produced closer to the star, and the weight of magnetic field strength is higher, and the lower frequencies are produced farther away from the star. And in the cases where the magnetic field topology is dipolar, the emission sites that corresponds to ECME at the same frequency, they constitute ring-shaped regions. And these rings are named as auroral rings. And ECME is directed tangential to this auroral ring, such that this direction of emission is almost tangential to the magnetic dipole axis. On the right, I have shown you an example of such radio pulses observed from an MRP, which is HT 15880. So these are real observation taken at around 700 megahertz. So here actually I have copy pasted the same figure 3 times just to convey the fact that these are periodic emission, not a transient phenomena. And these two colors represents the two circular polarization. Red corresponds to right circular polarization, or RCP, and blue corresponds to left circular polarizations. So another important characteristic of ECME is that it gives rise to very highly circularly polarized emission. And this oppositely circularly polarized emission corresponds to opposite magnetic hemispheres. For example, if the RCP is produced in the north magnetic hemisphere, then the LCP is produced in the south magnetic hemispheres. Although they have such widely separated sites of origin, they are still seen very close to each other because of the fact that this direction of emission is nearly perpendicular to each other. Now, these hot magnetic stars are not the only kinds of objects that emit this kind of emission. There are also other objects in our universe that produce ECME. For example, our own Earth produces this kind of emission known as the auroral kilometric radiation. Also, Jupiter produces ECME. Then there are other planets, and also there are ultra-cool dwarfs or UCDs that also produces this auroral radio emission by the process of electron cyclotron measure emission. Now, let me show you the most ideal signature of ECME in case of the hot magnetic stars. So here this circle represents this star, and this represents the dipole axis. N means north, S means south magnetic polar regions, and the rotation axis is coming out of the plane. And this is the observer, and this line of sight is in this direction. And these arrows represent the direction of ECME. I have already mentioned that this ECME is originally directed almost at right angle to the dipole axis, but because of the subsequent refraction in the stellar magnetosphere, they are deviated from their original direction of emission. That's why I have drawn these bent arrows. So when the star is in this kind of a rotational phase, the net line of sight magnetic field is slightly negative, and the observer will see the pulse that is produced or that is coming from the southern magnetic hemisphere, indicated by this blue pulse. After that, the line of sight magnetic field will become 0, and eventually it will become slightly positive. And then the pulse coming that is produced in the northern magnetic hemisphere will be seen by the observer. Then this line of sight magnetic field will increase and reach its maxima, and then again starts to decrease when once again this pulse that is produced in the northern magnetic hemisphere will be seen by the observer. And once again the line of sight magnetic field will become 0, and then it will become negative, and this pulse which is produced in the southern magnetic hemisphere will be seen by the observer for the second time. And after that, this whole cycle will be repeated. So basically, in one rotation cycle of the star, we expect to see 2 pairs of ECME pulses around this particular rotational phases where the line of sight magnetic field is 0. So these rotational phases are named as magnetic null phases. Each such pair of ECME pulses will have one pulse coming from the south and the other pulse coming from the north magnetic polar regions. And they can be distinguished from each other because, as I mentioned already, they will have opposite circular polarizations. So this talk is about the mystery of MRPs. In order to explain that mystery, let me briefly state the history of MRP discoveries. So the first MRP was discovered in the year 2000 by Trujillo et al. So they were observing the star Cu Virginis, which is a magnetic late B-type star, at 4 frequencies using the VLA. Their lowest frequency of observation was around 1.4 gigahertz. And at their lowest frequency of observation, they observed this very strong enhancement in flux density, which they confirmed to be a persistent enhancement. And these are observed near the rotational phases where the line of sight magnetic field is 0. In other words, they are observed near the magnetic null phases. Also, these enhancements were found to be very highly circularly polarized. So based on these properties, the emission mechanism was inferred to be the electron cyclotron measure emission. That is when this field of coherent radio emission from hot magnetic stars started. Following this discovery, for 15 long years, not a second MRP was found, not even a candidate. So basically, for 15 long years, Cu Virginis remained a lone MRP. In 2015, Chandra et al. Serendipitously discovered a candidate MRP, which is HG133880. This is also again a magnetic late B-type star. So they were actually carrying out a survey using the giant meter wave radio telescope at 610 megahertz, where their aim was to study this, the magnetosphere of the stars at sub-gigahertz frequencies, because before that, all the observation of these type of stars were confined to frequencies above 1 gigahertz. So their aim was to, so they basically observed this a sample of hot magnetic stars at random rotational phases, and in that study they found that one of these hot magnetic star HG133880 exhibits sudden or intense enhancement in flux density at certain rotational phases. Although they didn't have any circular polarization information or sufficient rotational phase coverage, nevertheless, based on the similarity of this phenomena which that exhibited by CU Virginis, they proposed that this phenomena or the emission mechanism behind this huge enhancement is ECME, which we confirmed in 2018 by observing the star for its one full rotation cycle using the GMRT at 610 megahertz. So we did observe huge enhancement in flux density, which is very highly circularly polarized, right at the magnetic null phase of the star. In the same year, a candidate MRP was proposed by or announced by Lang et al. 2018 from their circular polarization survey carried out with the Murchison-Whitefield array at 200 megahertz. And in 2019, the third confirmed MRP was found by Lato et al. 2019 using the VLA. So basically, within a span of nearly 2 decades, only 3 confirmed MRPs and 1 candidate MRP were found. Naturally, this led to the idea or notion that MRPs are rare objects. And this is where the problem started. It's because in order to produce this electron cyclotron maser emission, there are basically 2 primary ingredients. One is a strong magnetic field. I mentioned this word strong because the condition should be such that this at the region where ECME is produced, the electron gyro frequency should be larger than the electron plasma frequency. So that's why I mentioned this term strong. And also, the process requires an unstable electron distribution, sufficiently energetic unstable electron distribution. Now, these magnetic Early-type stars have, I already mentioned, they have kilogauss strand magnetic field, which are large-scale magnetic field, often of dipolar topology. So they already fulfill one of the requirement. In addition, they have strong stellar wind that acts as a constant supplier of electrons. So there is no scarcity of electrons. In addition, they also have magnetic reconnections going on in their magnetosphere, which can accelerate these electrons to the required energies. And because they have this dipole-like topology, that can facilitate the magnetic mirroring effect to take place, which results into a loss cone distribution, which can trigger the electron cyclotron maser emission process. So in other words, they seem to have everything that is required to produce this kind of emission. So hence they should be the natural emitters of ECME. Then why these MRPs appear to be rare objects? This was the mystery. In order to resolve this crisis, we decided to carry out a survey which will be dedicated to the discovery of MRPs using the upgraded giant meter wave radio telescope. So this survey started in the year 2019. And it was carried out in a frequency range of 550 to 900 megahertz, also known as band 4. And our sample included only the hot Mendel stars that have well-characterized magnetorotational properties. The reason will be obvious after a few slides. And so far, we have observed and analyzed data for 14 magnetic AB stars. Note that the survey is still ongoing. We are going to observe a few more hot Mendel stars in this current GMRT cycle. This current sample of hot Mendel stars, span the temperature range of 9.3 to 23 kilokelvin, mass range of 2.4 to 10.1 solar mass, magnetic field between 2 to 12 kilogauss, and rotation period between half a day to 4 days. But I'd like to confuse here that we just have one star that have a rotation period larger than 2 days. And in this aspect of rotation period, actually the interval or the range that we have been able to span is actually extremely small compared to the range of rotation period that these stars can have. So for example, they can have rotation period going up to decades, but due to practical limitation, we had to consider only those stars which are relatively rapid rotators. So it's because if the rotation period is larger, we'll require a larger amount of observation time to cover the same fraction of the rotation cycle. So we had to limit ourselves to the relatively rapid rotators only. Now let me show you the result. Before that, I'd like to remind you that this is the status of the field at the beginning of 2019 when we started our survey. So we knew of only 3 confirmed MRPs. And in the year 2021, we now know of 15 confirmed MRPs, out of which 10 were discovered from our survey. So basically, approximately 67% of the currently known MRPs were discovered by our survey. This includes one confirmation, which was the star HT142990 that was first speculated to be an MRP by Lang et al. 2018 from their MWA circular polarization survey. Now, the fact that we could find so many MRPs in such a short amount of time compared to this whole axis, x-axis, and so basically we had already mentioned that we completed analysis for 14 hot magnetic stars and we detected ECME from 10 of them. So this is quite a high detection rate. So naturally a question might arise, which is that whether we did something different, whether we did something new in our survey which enabled us or which enhances the detection rate of our survey. So in order to answer this question, I have listed here what was new with our survey. The first is the frequency. So this was the first observation campaign dedicated to the search for MRPs at sub-gigahertz frequencies. So previous search for this kind of emission were entirely confined to gigahertz frequency. So this low frequency or this sub-gigahertz frequencies remained a relatively unexplored phase space in the context of coherent radio emission from hot magnetic stars. Second is the observation strategy. So I already mentioned that our sample included only those hot magnetic stars for which we already knew the magnetic and rotational properties quite well. This was needed because we observed the star not for their full rotation cycle, not at any random rotational phases, but only around the rotational phases that encompasses this magnetic null phases. And in order to predict when this null will be observable, it was essential that we know the magnetic and rotational properties of the star precisely. This had the advantage of allowing us to observe a larger number of stars within a given amount of time. The third new thing is that we searched the signal in individual circular polarization, that is in right and left circular polarization instead of in total intensity or circular polarization. So it may not be obvious at this stage why this should be something very significant, because if the real signal indeed looks like this one, then if in total intensity or circular polarization in either of these two cases, this signal should be clearly detectable. And let me tell you that the ideal signature, actually what we discovered, could be very different from this. So let me explain why we decided to search the signal in RCP and LCP rather than in total intensity and circular polarization. So at the time, it was already, there already existed an idea, which was that the cause behind the separation between the oppositely circularly polarized pulses is not intrinsic to this emission process, but rather it appears because of propagation effects in the stellar magnetosphere. So here, this is the star, this is the dipole axis. ECME is produced almost perpendicular to this. ECME is directed almost perpendicular to the dipole axis. Here I have shown two frequencies, nu1 and nu2. Since nu1 is produced closer to the star, its nu1 is larger than nu2. And this represents the largest closed magnetic field line. Beyond that, the magnetic field lines become open because the wind kinetic energy is stronger than the magnetic field energy. So although they are produced almost parallel to each other, the different frequencies are produced parallel to each other or directed parallel to each other. Because of refraction, they get deviated. And larger this reflection, the larger will be the separation between these oppositely circularly polarized pulses. Now it can be shown very easily that as we go to higher frequencies, this deflection will be smaller and smaller. And hence, as we go to higher frequencies, even in the most ideal cases, we expect that the oppositely circularly polarized pulses will come closer and closer to each other, and eventually they will overlap, which will result into a very weak Stokes-V signal. So in order to be in a safe side, we decided to look for this phenomena in RCP or RCP and LCP rather than in Stokes I or Stokes V. Now, what are the implications of our results? So now that we have a reasonably large sample of MRPs, we decided to examine what fraction of these hot magnetic stars can produce electron cyclotron major emission. So we considered only those hot magnetic stars which have properties or stellar properties lying in the range that is spanned by our current sample of MRPs. And using this strategy, we found that at least 32% of these hot magnetic stars produces this coherent radio emission. This lower limit is already a large number in order to rule out the notion that MRPs are rare. So what we found from our survey, or what our survey results suggest, is that the MRPs are not rare in contrast to what had been thought. This automatically solves the mystery that the knowledge that we had regarding these hot star magnetospheres and the expectation that we had based on that knowledge was inconsistent with the observation that very small number of these hot magnetic stars produces ECME. Now our observation is not inconsistent with the expectation that we have from this hot star magnetosphere. In fact, now there is a real possibility that indeed these hot magnetic stars, or indeed most of these hot magnetic stars, are MRPs. But for that, we still have to continue our survey to find out more and more of MRPs. Now, a more relevant question will be to understand under what condition a hot magnetic star becomes unable to produce this coherent radio emission. The problem in answering this question is that not a single confirmed MRP is known. So our survey is also unable to produce a confirmed non-MRP. It's because we observe each of these stars only over a narrow range of rotation cycle. So there is no guarantee that these pulses do not lie just outside our covered rotational phase window. So this is actually the primary limitation of our survey. And without that, if we do not know a sample of non-MRPs, it becomes very difficult to understand what is different between the sample of MRPs and sample of non-MRPs. Nevertheless, now the fact that we have been able to discover a relatively large number of MRPs have enabled us to obtain a clue to understand what might switch off the phenomena in hot magnetic stars. And that clue was obtained when we tried to find out any correlation between the ECME luminosity and stellar parameters. We found the tightest correlation of this peak ECME luminosity with the surface temperature and the maximum magnetic field strength. With temperature, the relation is like a parabolic one. It reaches a maxima around 16 to 17 kilokelvin, and then it decreases. With magnetic field, it monotonically increases. Based on this observation, we constructed a quantity which we call as X, given by P0 by T minus T0 whole square, where T is in kilokelvin. And T0 corresponds to the temperature where this relation reaches its peak. We determined the value of T0 by maximizing the correlation between the peak ECME luminosity and this quantity X, and T0 came out to be 16.5 plus minus 0.5 kilokelvin. So based on this preliminary exercise, this is what we are calling as the X factor of hot magnetic stars in order to become an MRP, given by this dysfunctional form. And we found that this peak ECME luminosity varies almost linearly with this X factor. I apologize at this moment because I forgot to mention why I have used two different markers. So the circle, this represents represents data at frequency 700 megahertz, but for two stars we did not have observation at sub-gigahertz frequency, so we used the whatever observation that was available for these stars, and these two actually corresponds to data at gigahertz frequencies. Now, based on this relation between the peak ECME luminosity and the X factor, we can now say that when a star have a large value of X factor, it's more likely to be an MRP and vice versa. So basically non-MRPs will be the one which have a very small value of X factor. But before we start making this kind of a statement, it will be extremely important to find out whether this functional form of this X factor is robust. So to do that, we will have to make more discoveries of MRPs that will span a larger stellar parameter phase space, for example, a broader rotation period range, etc. And once we find a robust functional form of this X factor, it will be then important to understand what leads to that particular form of the X factor. For example, in this current functional form of this X factor, it is very curious, or it will be very interesting to understand why the T is equal to 16 to 17 kilokelvin should be a sweet spot for producing coherent radio emission from hot magnetic stars. Now, before I conclude my talk, I'd like to spend a few slides explaining why we should care about MRPs. So it's because what we have found or discovered recently is that ECME, this emission that characterizes MRP, it encodes information regarding the 3D density distribution in the hot star magnetospheres in the form of frequency dependence of pulse properties. So here, for example, I have shown you some simulated light curves at 4 different frequencies. This blue corresponds to ECME pulses that are produced in South Magnetic Hemisphere, and red corresponds to ECME pulses that are produced in North Magnetic Hemispheres. And this dashed line represents the variation of the line of sight magnetic field as a function of rotational phase. When there is not any significant density gradient surrounding these hot magnetic stars, this is how we expect the ECME pulses to vary as a function of frequencies. So only change is that these two oppositely circularly polarized pulses come closer and closer to each other as we go to higher frequencies. However, when there is a strong density gradient in these hot stars magnetospheres, this is how the ECME pulses might get affected. So a large number of aspects of this, or a large number of characteristics of these ECME pulses can get affected because of these propagation effects. And since this emission is so sensitive to this density distribution, 2D density distribution, it can be used as a stellar probe or as a stellar diagnostic in conjunction with other diagnostics that are already in use, like H-alpha emission. In addition, we have also discovered most recently, which is that this electron cyclotron major emission, this is the only kind of electromagnetic radiation produced by these hot magnetic stars that has the potential to allow us to get a zoomed in view of this stellar magnetosphere, something that no other known stellar probe can offer. So since I do not have sufficient time, I would not explain it further, but if anyone is interested, I will be more than happy to explain or discuss it later. Now the fact that we have discovered that these MRPs are not rare, it significantly enhances the relevance of ECME as a probe for hot magnetic stars. But all these things will be possible only after we succeed in fully characterizing this phenomena. And for that, it will be extremely important to continue our effort to discover more and more MRPs. And here are my conclusions. The phenomena of production of radio pulses via electron cyclotron major emission is not a rare event among the population of hot magnetic stars. Rather, there is a possibility that this is a ubiquitous phenomena among this hot magnetic star population. So it naturally solves this decades-old mystery regarding these MRPs, regarding these hot magnetic stars. We also found that the two stellar parameters that play a role in controlling the efficiency of the phenomena are the magnetic field and the surface temperature. But we have to do more discoveries to find out how robust these conclusions are. And in the future, as I mentioned already, it will be important to examine the robustness of these results with a larger sample, and also to understand the condition under which a hot magnetic star fails to become an MRP. Thank you for your attention.
All right, so a round of applause for Barnali. Chi's on the line, so we can take some questions. So I see Joe, you've got your hand up. So
yeah, Barnali, hopefully you can hear me. That's a really awesome talk and great work there. I just have a quick question about a couple of things. How many of your sources that you've detected in the radio, how many do you actually see periodicity actually returned several times and expected the pulse, or you only done it once? It wasn't quite clear in the talk.
So So in our survey, we couldn't observe each of them multiple times, but we did followed up a couple of them more than once. So that includes 1, 2, 3 out of these 10 discovered, we have observed 4 of them more than once, and in each cases we observed them right at the phases that we have observed in the previous time.
Yeah. It's an interesting problem. We're seeing this with some of the active stars in LOFAR that they look highly circularly polarized, but we're now questioning whether it's ECMI or not with these more active stars. And so that's why the periodicity would be really interesting here. Have you considered just post factor putting these things on the Goodall-Benz relationship and seeing where they exist?
Yeah, so I haven't done that, but this has been done for other MRPs by I think Lato's paper, where it was found that they actually deviates from this relation in the same way that this ultra-cool dwarfs does.
Yeah, great. Yeah, no, it would be great to see it for your large sample now, because you have big number stats, and almost all these things will probably be in ROSAT, right? So it's a reasonably straightforward thing to do, and it would be interesting just to confirm what's going on there, because the thing that threw us with the active stars in LOFAR was that they all follow the Goodall-Benz relationship in a way we didn't expect, like the M dwarfs don't, as I showed in my recent paper. But anyway, that's something we can discuss offline. It was really nice work, Barnali. I don't know if Harish is online. He might have something similar along those lines.
Yeah, so any more questions? Oh, yeah, Harish.
Yeah, I'm here. I missed a small part of it, but I heard most of it. So my question was about the modeling. So you said that you put in refraction and then try to get the geometry out of all of and match the radial light curves. How much of that is known in the sense that you need to know the plasma density in the closed field region to calculate the refraction? Yeah, is there an assumption there, like a reasonable assumption, or is that something that is known based on other measurements?
Yeah, that's a great question. And this is something that we are planning to do in the future in a more robust manner. So there exists some semi-analytical model that predicts how the density should behave around in a closed magnetic field region. And our model was currently, the simulation is a preliminary one in the sense that we have assumed a very idealistic dipole magnetic field, which is not true. So our whole aim was to check if we consider this ideal case, and if we use this semi-analytical model that predicts the kind of density distribution, whether or up to what extent is light curves will be affected. And even in the ideal case, we found that it can get affected to a significant extent. Now we are actually collaborating with other people people who are working in the optical part. So they are doing MHD simulation and they are actually deriving some empirical relation to predict the kind of density distribution. And the important point here is that most of these things were done based on the H alpha measurements, based on how the H alpha varies. But the thing is that most of these MRPs, they actually do not show this H alpha emission, which means that there is no constraint available regarding their density distribution. But there does exist the prediction of how the density distribution should be for stars that produce H alpha emission. Now our plan is to use that kind of a distribution and apply on these stars and see whether the similar kind of density distribution is also valid for this kind of stars. So that's the kind of thing that we are planning to do in the coming years.
Got it. Is there time for another question? Oh, no, I think Hari should go ahead. And if there's time in the end, I'll ask another question.
Go ahead, Harry.
Hello, can you hear me?
Yes.
Yeah. So, Barnali, I was just thinking. So you mentioned that you're going to look at H alpha, but I was just also wondering if you'll be looking at HST observations. Maybe I guess FUV is also more sensitive to thermal plasma, and that could also give you a sort of better idea on the density distribution, right? Or would it be much closer to the star than what you're looking at?
You mean the do you mean the photometric observation, something like that?
No, yeah. So I was thinking about more like FUV observations.
Yeah. So and so actually, although there is not a direct kind of established relation, but things that the stars which do not show this H-alpha emission, they were also not seen to observe UV emission. I'm not very sure about this aspect because I do not really work on this aspect, but these models that in the optical model that exists, they actually account for this both UV variation, photometric variation, and the H-alpha variation. And the problem with this, most of this magnetic late B star, which are for where this most of the MRPs lies, is that we do not have those kind of information for them. But to be honest, I am not very sure about the UV emission because most of the time that it is the H-alpha emission that people usually put most of the emphasis. I'm not sure why, but I'll definitely would like to see. I mean, I will have to look into it in more detail. Sorry, I did I answer?
Yeah. Usually H-alpha is more sensitive to the activity, sort of an activity index. So I guess that's one of the reasons probably H-alpha is concentrated. So I was looking at it from a more solar perspective because
Okay.
EUV observations are usually much more useful to density and thermal plasma diagnostics. So I guess FUV should be useful to do a similar thing on hot stars.
Yeah, I'll look into that. Thank you.
All right, so that brings us to the end of our session. And so let's thank all the speakers again. And so up next will be convening or moving to GatherTown for a discussion. And I don't know, Joe, if you have are there any logistical things?
No, that's it. Just come and join in GatherTown, and otherwise ask questions on Slack. And yeah, GatherTown, go and look at the lightning talks and play some games in the lounge if you want with some friends. It's there's lots of space to have fun there. And yeah, let's continue the discussion in GatherTown.